Hello everyone. Let's continue from where we stopped in the last video. So we came up with some naming conventions for your voltages across NMOS and PMOS. We gave some unique names to it. We gave VDSP, VDSN, VGSP, VGSN and so on, just to differentiate the gate to source voltage between NMOS and PMOS. Okay, we did that for simplicity. And the second thing you observed was that the current directions are exactly inverse. So for example, this charging capacitor, if it has a discharge current in this direction, just look into this capacitor. This capacitor has got a discharge current in this direction to going towards upwards. The charging current for this particular capacitor is in this direction from up to down. Okay, so we have come up with these two conclusions in the last video, and these are very important ones in deriving the load curve for CMOS, or basically load curves for NMOS and PMOS, and then eventually merging them to get a final voltage transfer characteristics for your CMOS. Okay, so that's why we did all this. We converted few things over here. Now let's try to play with some equations. Let's try to get some equations, get some hands on the equations, and let's see how do we tune them to get the voltage transfer characteristics. When I say voltage transfer characteristics, it's purely a function of voltage. Okay, we have to identify whenever the input voltage rise. For example, let's say take a case of an inverter. Take a case of this particular gate. Let's say this was not an inverter, it was a NAND gate or a NOR gate. Okay, so everything that we go around digital circuits, that's based on voltages. What is the input voltage you provide and what is the output voltage you get? So it should be all be a function of V out and V in, and that's why the CMOS voltage transfer characteristics has come into picture. Okay, and that's why it becomes very important to do it. So let's move on. So we will play with some equations. We know that by observation, if you observe this piece, if you observe this NMOS piece of circuit, okay, what you observe over here is your VGSN. Your VGSN is this point minus this point, which is V in minus VSS. Okay, and that can be just, since VSS is 0 volts, VGSN can be directly plugged as V in. That's the one very important observation. The second one, your VDSN, again we are just restricting ourselves to the NMOS discussion over here. So your VDSN, which is from this point to this point, it's just plain V out. Okay, things are still simple because we are in the NMOS region whose one of the terminals are connected to ground. So things are still simple over here. The complexity arrives when we actually enter into the PMOS description of the same thing. Okay, it's not so complex, but still there are some additional parameters that comes when we try to analyze PMOS in this scenario. So let's do that. So in this case, VGSP is V in minus VDD. Okay, it's whatever so in this case, VGS calculating of gate to source voltage was pretty simple because one of your terminals was connected to ground. In this case, it would be a bit difficult because we have to, while you change your input voltage, you have to constantly keep on subtracting the VDD from it to identify whether the gate to source voltage is negative, and it should be less than the threshold voltage of PMOS for your PMOS to turn on. Okay, so things becomes a bit tricky over here. We just need to be a bit careful, an extra careful over here. So so VGS is not just V in over here, it's V in minus VDD. Okay, so that's what VGSP we have. And VDSP, which is a difference of voltage from this node to this node. Again, you go in this direction as per Kirchhoff's law. So you have VDSP as V out minus VDD. That's what we have mentioned over here. So VGSN and VDSN were simple, but VGSP and VDSP are a bit critical because every time you need to subtract an additional potential from your VDSP and VGSP calculations. Okay, so we'll try to go slow and keep things simple, more and more simple over here. One more observation that we talked about just in the beginning of this video is the drain current direction. Okay, in this case, IDSP is negative of IDS, and because if you observe the drain current flow in this capacitor itself, they are in opposite directions. Okay, so we have this one more important observation, which is IDSP is negative of IDSN, and these are the only things that we need to derive your drain current. Eventually we will not even need the current values over here. We'll just play with this particular equation and try to come up with something that will convert into voltage form. Okay, so let's try to do that. So that's all we needed from the observation side, observation point of view. So let's push it over here and we'll try to derive the load curves one by one. So first of all, we'll start with the basic and simple one, where we had some time back we had done some spice simulation on getting the IDS versus VDS curve for NMOS. Okay, we did that in the past, where we actually tuned your gate to source voltage at different points, and swept the VDS, sweep the drain to source voltage, and got some drain current equation. So it looked something like this. I've just taken one example over here. So it looked something like this. You had the IDSN axis, you had the VDSN axis, and at varying gate voltages your current was increased. So for example, VGSN1, it's this one. If VGSN1 is one of the gate to source values for NMOS, let's say it was at 0 potential. So in that case, you see your drain current is almost equal to 0. Okay, because since VGSN1 at 0 potential, it itself means that your NMOS is off, it's below threshold voltage. Okay, moving on, when you increase your gate to source voltage at some sufficient value, at a point which is just above the threshold voltage, in that case your NMOS turns on and you actually see some current flow, and as a result of that you see this particular load curve. And this curve we have already talked about in the past videos, so let's not spend more time over here. Okay, and next, same thing you do, you just increase your gate to source voltage for your NMOS, you see an increase in the current. And we'll do the similar thing, we'll go on doing it till we attain the maximum saturation voltage over here, the highest VGS value that can be attained. So VGSN4 and VGSN5. So these are the curves that we had seen in couple of videos, and we have also done some simulations. You might want to have a look into those videos. Okay, so this is the curve, this is the NMOS IDS VDS curve. Okay, let's try to plot a similar one for PMOS as well. Okay, PMOS is a bit tricky. The one clue that you can get over here is all your drain current for PMOS will be an inverted form, all will be negative of IDSN. So if you see a positive current over here, the value of the current will be negative. So you will have something from here itself. It is very much easy to get that the IDSP curve will be somewhere in this particular quadrant. Okay, so let's do that. We'll draw the PMOS versus PMOS IDSP versus VDSP curve, and it will look something like this. You have your IDSP as negative because it's inverted form of your IDSN, and there are reasons, the flow of the electrons and the potentials that you apply for the PMOS. That's the reason you see a negative IDS. In general, current can't be negative, current values can't be negative. It just because of the direction of the current flow. Okay, so negative IDSP in perspective of drain current of NMOS. Okay, that's why the PMOS current is negative. Okay, so we have and the negative VDSP, because again it's in perspective of your NMOS, because what potential you apply at NMOS for getting the MOSFET turned on, you have to apply the reverse potential for PMOS for getting it turned on. So that's why it's a negative potential over here. So let's draw the load curve. You will have negative VGSP1, which is basically say it is similar to VGSN1, though the values will be different. The threshold voltage values for PMOS and NMOS are way different because your NMOS and PMOS, because of the mobilities of NMOS and PMOS. I'll come to that part when we enter into device physics course. But in this case, if you see the VGSP at negative VGSP which is less than negative VT, and negative VT is the threshold voltage of your PMOS turns off and there is zero drain current. Okay, and as and when you try to increase your negative VGSP, or basically VGSP towards more negative side, it becomes more and more lesser than the negative threshold voltage of PMOS. By the way, the mod remains, that's why we go by the mod concept, where its mod of VGSP should be greater than mod of VT. So that way things become simple. But from a precise description point of view, let's keep things as it is. So negative VGSP is less than negative VT, which means that your PMOS has already crossed the threshold voltage level, which is the surface inversion voltage, and as a result of that you see some drain current flow for your PMOS as well. And similarly, you increase your VGSP to some higher values and so on, and to the fullest value you will see the maximum drain current sitting over here. Okay, so these were the two curves. This is the one which we had simulated. This is the one which we didn't simulate, but you can just replace your NMOS by a PMOS and you can get these curves very easily. Okay, so these two curves are the very important ones in deriving your voltage transfer characteristics for your inverter. So what we'll do is we'll use these curves, we'll try to play around some voltages, we'll try to play around with these curves. So we have these equations, we have this observations, and with using this and this, we'll try to play around with some with these graphs and with some voltages, and try to get the load curve or the voltage transfer characteristics for your CMOS inverter. So let's try to do all this in the next video. Thank you.